Okay, this is part 2, so make sure you've watched part 1. I'm picking up with boundedness on this one. So boundedness is basically like there's some sort of barrier that's preventing the graph from going higher or lower. It is bounded, like a boundary. So above, at the top you can see, these are on your paper, the first graph is not bounded above or below because it goes up forever, it goes down forever. Even though it has the gap in the middle, it goes past that gap, so it keeps going up and keeps going down. The second one, it goes up forever, so it's not bounded above, but it is bounded below because it never goes below this point right here, which we would call a minimum. On the third one, it never goes above. These look like they're even points, but there is a maximum there that it does not go above, so it's bounded above, but it goes down forever, so it is not bounded below. And then the last one, it never seems to go above. I think this one's a little bit higher, but there's a maximum, it never goes above, and there's a minimum. Those look like they're about the same, but it never goes below, but there is a minimum. So it is bounded both above and below. We just call that bounded. If you wrote out above and below, like I'm not going to take off, but that's what bounded means. So to look at these, I can picture what this graph looks like if I want to, which we'll get more practice with this in the coming days. But on A, this is a parabola that has been shifted down 4 and stretched, but my normal parabola has like a minimum. All I've done is move it down, so I should be bounded below. See, I've put in a picture of this so I can look. Oh yeah, there's a minimum down here, so it's bounded below, but it is not bounded above, so simply bounded below. You do not have to tell me that it is not bounded above. You can just say bounded below, and that's fine. On B, we have not really worked with this one a whole lot. This looks a little bit weird, so I'm going to head over to my graphing calculator, and I'm going to graph that, and this is what I get. And it does seem to have like this little bump down here on the bottom, this little bump up here on top, and everything is kind of staying between the two of those. So it is bounded above and below, which again we call simply bounded. Now, those things that are the boundaries, I've already kind of called them minimums and maximums. Their general name is actually extrema. So there are local and absolute extrema, or what I typically call instead of local is relative. They're the same thing. It's just relative to that area or localized to that area. So it's a minimum or a maximum for some section of the graph. However, if it's the absolute highest or lowest that the graph goes, it's called an absolute extrema, or an absolute min, or an absolute max. So relative means like it's the lowest I go in that section and I turn back up, or maybe the highest and I turn back down. But at some point later in my graph, I might go higher or lower than that. So for example, we want to determine whether this graph, x to the 4th minus 7x squared plus 6x, has any local maxima or local minima, or any local extrema, one might say. So graph that on your calculator. Pause if you need to, because you're going to have to use your calculator for this one. Your graph should look kind of like this. Actually, probably you don't see this bottom minimum. Try zooming out a little bit so that you can see it. It does not have to be the exact same window that I have. You simply just need to see it. I have a minimum down here. I need to figure out what, and I'm going to go left to right across my graph. That's how we always kind of read graphs, whether we're doing increasing and decreasing or minimums and maximums. And I've actually had a look at this. I'm decreasing, I hit my minimum, I'm increasing. So whenever it changes from increasing to decreasing or vice versa, you will have a minimum or a maximum. So to get the coordinates of this point, we're going to do this very much like how we found zeros or our x-intercepts on our graphing calculator. So you're going to go to second, calc, and then you're actually going to hit minimum or maximum, whichever one it is that we're looking for. In this case, it's the minimum. But it's going to ask the exact same questions that we did for x-intercepts. Left bound, so move your little blinky cursor guy a little to the left. Right bound, so move your little blinky cursor guy a little bit to the right. And then guess, and you're going to get as close as you can to that minimum, and then hit enter, and it should give you this exact value. And you're going to say that your minimum is at negative 2.06, comma, negative 24.06. Round to 2 decimals is fine. You can write them all out, but you do need at least 2 decimals. You should not be rounding all the way to negative 2 and negative 24. You are going to do the same thing for your maximums. So the maximum looks like it's right about here. I'm going to go second calc max, left bound, right bound, guess, Do the same thing for the minimum. Take a second and do those. For my maximum, I got 0.46, comma 1.32. For my minimum, I got 1.60, negative, or comma, negative 1.77. So the first minimum is the absolute lowest the graph goes, so he would actually qualify as an absolute minimum. Whereas this little max in here and this little min, like the graph goes above that maximum, and the graph goes below this minimum, so they would be considered relative maxes and mins, or local maxes and mins, because they are a maximum or a minimum for just that one chunk of the graph. Next, we're looking at symmetry. So that's like if I folded my graph in half maybe, or if I turned it. So we have even symmetry, and technical definition there would be for every x in the domain, like it actually works. If I plugged in, let's say, f of negative 2, or if I plugged in f of positive 2, I'm going to get the same answer. So whether I use a negative 3 and a 3, or a negative 1 million and a positive 1 million, or a negative 8.7 and a positive 8.7, I'm going to get the exact same answer. You may want to add this on your paper. It is symmetric over the y-axis. So the y-axis goes straight through the middle of your graph where you could fold it over that. Your odd functions mean that if I plugged in, I'm just going to start with a negative 2 again. If I plugged in a negative 2, I would get the same answer as if I plugged in 2 and then changed the sign of my answer. So if I plug in negative 2 and get 5, and then over here I'd plug in 2 and I'd get 5, but then I'm making that negative to get the negative 5. So you get the same number, the same value, but one answer is positive and one answer is negative. Whether you're plugging in a 2 and a negative 2, a 6 and a negative 6, an 8.7 and a negative 8.7. It is, add this to your notes, it is symmetric over the origin. It is actually a rotational symmetry, so like you take your graph, turn it 180 degrees or turn it upside down, and it looks exactly the same over the origin. So we have a couple of examples. For these, we're going to start by just graphing them. So for A, let's graph this parabola. I have this nice, pretty parabola, and if I look at this on my calculator, it looks like the y-axis goes straight through the parabola, straight through the middle of it. It cuts it in half, which makes sense because it was my basic parabola shifted down 3. He is even. I'm going to move him down to my bottom so we can look at the second one. X squared minus 2x minus 2. So this minus 2x in the middle is changing something with my graph. It looks like it's kind of been shifted to the right a little bit. And I can see, yeah, my y-axis doesn't go straight through that one. So that one is not even. Also, if I turned my graph upside down, it doesn't look exactly the same. So he's not odd either. He's considered neither. Most of our graphs are going to be neither. Some of them have this special symmetry. So I moved this graph down here so that you could see it. This is the third one. He looks all sorts of crazy. Make sure you're able to type this into your calculator and get this picture. But if I look at him, like, I'm going to start with my y-axis first. He does not cut him right down the middle. Like kind of like he's cutting him in the middle, but like it's not a fold line. If I folded this guy over, he'd be over here and there's nothing there. So if I actually take your calculator and turn it 180 degrees, compare it to my graph and what you have now upside down, they should look exactly the same. So you have turned it 180 degrees and it landed back on top of itself. That is odd type of symmetry, so odd symmetry. So A was even, B was neither, and C was odd. We have two more sections we're going to cover. Both are things you have seen in Algebra 2. Asymptotes, so that is when you have like some sort of line that the graph approaches but never actually hits. Horizontal asymptote means like it going flat left and right, like the horizon or a horse's back. The line y equals b, so it's going to be y equals some number whenever you have a horizontal asymptote. It's an asymptote of the graph of some function if that function approaches that value as you go to the right or to the left. So we'll have to look at this a little bit. If you don't remember this at all, but again, this was Algebra 2 stuff. There are some rules for these. These happen with your rational functions. So that would be when you have a fraction as the function. Yobob means that your horizontal asymptote is y equals 0 if the exponent is bigger on the bottom. Nobot, so these are all shortcuts that we use, means that you have no horizontal asymptote. It does not exist if the exponents are bigger on top. The coefficients mean that if the exponent's the same on top and bottom, so like not bigger or smaller, then you look at the coefficients. So if I had like 2x squared over 3x squared, I would use their coefficients of the 2 over 3, and my horizontal asymptote would be y equals 2/3. Again, we'll get a little more practice with these, but you definitely want your rules written down so we can talk about them. For your vertical asymptote, so that's going to be a vertical line straight up and down, x equals some value if my graph is approaching that value from the left and the right. This happens when, again with rational functions, whatever number makes your denominator equal 0. So we kind of looked at this. This was a type of infinite discontinuity earlier. And I talked about that was when you had your denominator equal to 0. So for this problem, I want to identify any horizontal or vertical asymptotes of the graph. So the first thing I'm going to do is my horizontal. With your horizontal, you're looking at whether it's the exponents are bigger on bottom or bigger on top or the same. So my exponent on the top is 1, my exponent on the bottom is 2, so 2 is bigger than 1, so my bottom is bigger. Bigger on bottom, that's Bob. So yo Bob means that my horizontal asymptote is y equals 0. That's what the yo part is. So you're just going to write horizontal asymptote y equals 0. There's really like not even any work to show for that. Now for your vertical asymptote, there is work. You need to set your denominator equal to 0. So when you set that equal to 0, that's a quadratic. We did these last chapter. That factors. That should factor to x minus 2 times x plus 1, which means I'm going to get x equals 2 and x equals negative 1. I have two vertical asymptotes, and if you look at the graph, you should see like a weird gap at x equals negative 2, x equals positive 2 and x equals negative 1. That's where I'll have vertical asymptotes. And I should see that for my horizontal asymptote, like the graph, never really, like on the ends, it doesn't actually hit the x-axis. It just gets really, really close to the x-axis on the ends. The very last thing we're actually going to look at is the ends of our graphs, the end behavior. All right, so end behavior is the ends of my graphs. Describes how the graph behaves on each end. I know, terrible definition, but we're going to look to the right of our graph and we're going to look to the left of the graph. It does not matter which one you do first. However, there is a neat trick I'll show you in a second if you start with the right. So when you are writing your notation, looking to the right is as x approaches infinity, because that would be as I look to the right, my x value is getting closer and closer to infinity. F of x is approaching and then either infinity or negative infinity. It's either rising and going to infinity or falling and going to negative infinity. Same thing for looking to the left, but it starts as x approaches negative infinity, because to the left is negative infinity. So for this example, we're going to just graph this function to start. X to the fourth minus 2x squared plus 2x plus 3. And I'm going to start by looking at the right of my graph. So as I go to the right of my graph, oh my god, it's going up. It's going up and up and up and up and up and up forever. So my graph goes to infinity. To the right. As x approaches infinity, the graph approaches infinity. Now looking to the left. I'm going to go left. Oh my god, it's going up and up and up and up and up and up and up to infinity. So my graph approaches infinity. Now this is great if I'm looking at the graph. If I don't have the graph in front of me and my evil pre-cal teacher doesn't let me use a calculator, graphing calculator, I have to just look at this function. So to start, you're going to look at the leading coefficient. So whatever the number in front of your highest powered term is, which in this case there's no number there, that's not 0, that's 1. Remember, you don't have to write the 1. So because that number is positive, so because my leading coefficient is positive, in this case it was a 1, the graph will rise to the right. So any positive number would make it rise to the right and go to infinity. Any negative number out front would have made it fall to the right and go to negative infinity. So that gives me my right side, the leading coefficient test. Once I have the right side, I then actually want to look at what that exponent is. So in this case it's 4, and I don't care whether it's positive or negative because my exponents are pretty much always going to be positive once I've written them out. But I want to look at the fact that it is even. So because it's even, they actually go the same direction. So because the right went to infinity, the left goes to infinity. If it was an odd, they would go opposite directions. And it might help to think about y equals x squared, they both go up. Y equals x cubed, one goes up, one goes down. Thank you guys for sticking with me for all of these notes. I'm sorry they're so long.